Okay, so over the last couple of days, I've been teaching you guys about what one equilibrium is, and hopefully you now have a fairly good definition in your mind of what equilibrium is, but also what it is not. Equilibrium does not mean that you have 50% products, 50% reactants. It means that as your products turn into reactants, or your reactants turn back into products, really, however you want to describe those, that the rate is the exact same. I love the analogy of the ants carrying rocks from one pile to the next. Okay, from a microscopic point of view, you would see things happening, yes. But from a macroscopic point of view, you don't notice anything happening whatsoever. Does that make sense? And so as long as that rate is the same, it's consistent. And what this leads to then is some issues with if you want to produce something, like for example, that Haber process we talked about. Let's try a new page here. If you want to take some H2, add to some N2, and try to create some NH3, that's fantastic, but you might only create, say, 17%. And the reason why is that for a little while here, the forward rate works pretty good, but then eventually the forward rate kind of decreases because the reverse rate starts to increase, and eventually it levels off. Right? And as soon as the rates are the exact same as each other, well, now you're at equilibrium. And so that's why we draw the arrow going backwards. So now one of the things we did discuss, and I showed you in the lab yesterday, is the idea of you can make a shift, you can make an artificial change to the system by doing one of three things. You can either change the concentrations of your reactants or products, you can change the temperature of the system, or you can change the volume of the system. So I know you guys don't have this slide with you, but here's an old diploma question. Why don't you take a look at it, see if you can answer it without me talking about it? Because there's really no work to it. This one's not in your slides, right? Give this one a try. So let's walk through them one at a time. Okay, so if you increase the pressure by reducing the volume, you're changing how much room there is. There'd be less room. On this side, there's two molecules of gas. On this side, there's two molecules of gas. What would happen if you changed your volume? Nothing. Because there's really no better side to move to. If you had a 3 to 2 ratio, then it would move to the 2 side if there was less space. So A is not going to accomplish anything. What if you removed nitrogen monoxide? So I like to, when I do this, I draw like a down arrow here, basically saying there is a lack over here. So somebody just got robbed. That's the analogy I might use. This guy just got robbed. And over here, these guys heard about that and said, oh, that sucks. We're going to start a GoFundMe page and we're going to increase our rate of reaction so that this rate takes over a little bit. Now, eventually over time, although the reaction rates won't be equal, eventually this one will kind of catch up again. But for, at least for a time being, it would have shifted this way, but that wouldn't make more nitrogen. That would make less of it, so that doesn't help. What if we were to add some oxygen? Well, the analogy I use here is this guy just won the lottery. Oxygen just won the lottery and is now very generous with its money. It says, I have so much, I am going to give it away. And so its forward reaction rate increases a little bit more. And you know what that ends up making have happen is oxygen gives away a little bit of its money, and nitrogen kind of comes along for the ride and says, oh man, if you're going to be generous, I guess I better be too. And so it gives up a little bit so that we can make a little bit more over here. So the shift there, but yeah, again, in this case right here, that didn't actually make more nitrogen. So for the last one then, the last one's the right answer. By the way, did any of you guys get the last one? D without, okay, me saying it? So if you were to decrease the temperature, what you're doing is you're causing a lack in energy. And so now this energy's gone down. And really what your equilibrium is going to do is it's going to try to balance that by heating it back up again. And the way it's going to heat it back up is by trying to shift this way to produce more of this heat. It'll try to produce a little bit more heat. It'll also produce more oxygen and nitrogen along the way. And that's its like self-balancing. And that's where the name equilibrium kind of comes from, right? Is that it wants to try to refine its balance state. So yeah, decreasing the temperature would have done that. You guys think you can handle something like that? Okay. No. Do I need to try another example? Okay. You just shook your head no, so. Okay. I'll try to find another example at a later date. One of the other things I need you guys to be able to do also is do one of those ice tables. Okay. Let me give an example. Let's say that I told you that the Kc value for an equation was, let's say, 0.57. And let's say that I told you that you began with, let's say, 2.00 moles per liter of hydrogen iodide, and it's going to decompose. I might ask you, how much iodide gas will you make? So this is this would be the other kind of thing we've worked on so far. So the first thing I'd recommend you do then is you'd want to then make yourself kind of an ice table, but you need to have your balanced equation. So if you're starting with hydrogen iodide and it's going to decompose, it'll turn into H2 and into I2, and you better have two of those. How much is the max amount of iodide that you can make? How much is the most iodide you could possibly make? If you started with 2 moles per liter of this, how much of this could you possibly end up with? Grand total of 1. That's the best you could do. However, just like in some of our other equations I've shown you, what if the yield is only like, say, 17%? I don't know that it actually is 17%. I do know that with a Kc value less than 1, though, it definitely is not over, it shouldn't be over 50, hopefully, right? Like, we should have a low yield here. Okay. So, based on the fact that this stuff is going to start turning back again, we make one of these ice tables. Right, so you'd start with a 0 here and a 0 here. You guys remember what to do next? Yeah, because I don't really know how much iodine I'm going to make, so let's call it x. How did it get there? Well, 0 must have went up by x, and 0 must have also gone up by x. What happens in this column? Yeah, because it must have gone down, and however much this guy gains, well, the 2 to 1 relationships means that this must go down by 2x, so you're left with 2 minus 2x right here. I'll have to put a new page in, I think. Give me a second in case anyone wants to write this down, though. Well, if we know the Kc value and we know at least the framework right here with algebra, I can't promise this is going to be a nice step, this next one here, but it's a math question now. We need to then write our Kc equation, and since our equation was 2 hydrogen iodides forms 1 iodide and 1 hydrogen, your equation looks like this. Hydrogen's concentration, iodide's concentration, all over your hydrogen iodide, but because there's a 2 in front of it, you got to square it. Does that ring a bell? No, it's been since the long weekend. But that's known as your equilibrium constant equation. So then if I go back a slide here, I just need to throw in all the concentrations, which I don't even know, they're just variables. So this one here is going to be x, this one's going to be x, this one was 2x, no, it was 2 minus 2x, and we'll square it. And since I told you the Kc value was 0.57, we can now solve for x. I pointed out to you guys earlier, they give you the quadratic formula in your data booklet. I don't think that's ever by accident. That being said, if you need to, you can also graph this to solve. Here's how I'd solve this one myself, by the way. I would say that you have 0.57, and it equals 2 minus 2x, but that's all squared, right? But isn't your x's also squared? So on this one here, I can actually play a nice little trick. I can just square root both sides. And what I'll end up with then is x over 2 minus 2x, and then this side over here will be whatever the root of 0.57 is. I don't like this new program. I can't go down. Used to being able to slide down. So you'll have to move that over to this side right here. Anyways, I'm not going to solve the whole thing, but do you guys kind of get the way of how you'd solve for x from here? you'd end up getting like, well, you'd get 2 times 0.57 minus 2 0.57x equals x. You'd bring that to the other side, you'd divide, and you get your answer. So really that's it. That's what we've learned so far, those two concepts. Being able to make an ice table and make predictions based on Kc values, and being able to work with Le Chatelier's principle. Okay. My goal today now is to bring this equilibrium concept to probably the most common place we're going to use it, acids and bases. Okay. We actually began our year. There you go. We began our year back in Chem 20 talking about acids and bases. And this actually led to our talk about the pH scale. Do you guys recall that the pH scale goes from roughly about 0 to 14? It doesn't actually go from 0 to 14, but the number that's really important is the one right in the middle, 7. You guys remember why 7 was the pH of water? It's been a while. Remember why 7 is the pH of water? Is water actually pure water? 2 times in a billion. It's been a long time, but 2 parts per billion. What ended up happening is that whenever you had a water molecule, it would actually break itself up into H3O plus and OH minus. You actually needed 2 of them for this to happen. Do you guys recall this? Anybody want breakfast? Or at least like motioning outside here. We've got really yummy looking muffins actually. Cheese, yogurt, fruit. Thanks, Marley. Thanks. Okay, so from our review from Chem 20, way back in September, I know it's been a long time since then, but we discussed how 2 water molecules in a billion will actually break up into an acid and a base. But what I wasn't really able to describe way back then was that they don't stay that way. Because really what happens is these water molecules, sure, they start breaking up into acids and bases, but let's say that that's what always happened. Well, eventually you'd have a solution of half acidic molecules and half basic molecules. But what really ends up happening is equilibrium takes place, and they start changing back to where you started from. Does that make sense? Now, if you were ever to look at a snapshot of how much acid you have there, it actually is discovered that 2 parts per billion ends up being this concentration, 0.0000, I think that's how many I need, 1 moles per liter. That's how many you'd have of your acid. And then guess what that turns into on a pH scale? pH means, you guys remember this formula? You have to negative log your concentration. And when you negative log this concentration, that's why water has a pH of 7. Apparently there's lots of distractions today. Yeah, they're sitting in the fume hood. Where? In the fume hood. Yeah. So that's where I want to actually kind of begin our topic today, is the idea that acids and bases, and very specifically water, that's actually an equilibrium system. When you guys look at just a basic water bottle, if I can kind of just draw a basic picture here, imagine this is your I don't know, cup of water, right? Most of us, we think, well, you've just got a whole bunch of water molecules sitting in there. And for the most part, that's true. But what can actually happen is these guys right here, they can collide into each other. And what it can end up producing is this one could become H3O plus and become acidic, because what ends up happening is a hydrogen moves from one to the other. And this one right here can produce OH minus and become basic. But let's say that that continually happened for forever. This would be horrible for our world, because there would literally be no water slowly over time. Even if this happened at a very glacial rate, slowly over time, all of our water would change into half acid and half base, right? But this made sense to you guys when I explained it to you way back in September, because really what's going to happen is eventually this H3O, these guys are going to go their own ways. This one will go that way. This one will go that way. Well, there's lots of water, right? So eventually this guy's going to run into another random OH minus that's been floating around. Again, there's only 2 of them in every billion. And what ends up happening here is then this one and this one will recombine to form waters again. Hence the concept of equilibrium. And I think I showed you guys this on your data table. Do you guys have your data books nearby? I'll try to pull one up on my screen maybe even. It'll have to be sideways because that's how mine shows it. Data book. There it is. So I'm talking about, we're going to finally talk about this slide right here. The ones that are sideways. I wonder if they can flip. View, rotate. Haha, there we go. Do you guys recall this table here? So what ends up happening on this table then is that water is actually the very, very lowest one on the table. And the reason why water is so low on the table is that, does water have the ability to be an acid? Yeah. But is it very common? No. 2 times in a billion. And you can actually kind of see this number down here is what we're going to talk about in a second. This is its K constant. We're eventually going to get into Kc constants. We've already discussed that. We're going to get into Ka constants and Kb constants. Those are constants specifically for acids and bases. But look at this number right here. It's 1 times 10 to the minus 14. Okay. Now, I want to consider the equation for water. If I were to write out an ice chart for water, which seems kind of silly, but what would it look like? Well, you'd have 2 water molecules, and it would turn into 1 H3O, and it would turn into 1 OH negative. Really, that's what we're trying to describe here. But does it stay that way? No, heck no. It goes back almost immediately, because this really occurs at like a 0.00001% of the time. It happens so rarely, which is good, right? 2 times in a billion. But if I were to actually try to like make an ice table out of this, here's how it kind of might look. We would actually consider the hydronium, and we would consider the hydroxides, like they would actually be given numbers. Water actually would not be considered at all. Does anybody know why we would not consider water in our ice table? I've only barely mentioned this, but I know I have talked about this in class before. It's a liquid. We can only consider things in an ice table that actually have a concentration. And there's only 2 states of matter that actually have a concentration. One is aqueous, the other one's a gas. What is concentration? It's how many moles you have per liter, right? Well, we can either change the amount of moles you have, or we can change the amount of liters you have. Now, you can change the amount of moles you have for aqueous solutions because you just dissolve more stuff. So aqueous concentrations can change. You can also change gases, not because you necessarily add more stuff, but you can change the volume of gases. Gases are compressible, but liquids and solids don't. So we actually can't even consider water in this, which is kind of odd then, because when you want to then consider the ice table, what essentially happens is you don't even consider this. And it started at 0, and it went up. And then the question is, well, how far did it go up? Well, we actually have been able to measure that. We know that it went up 0.00000001. And the reason we know that is because this is the number that when you negative log this number, it gives you a pH of 7. That makes sense? So a pH of 7, which is neutral water, gives you this number, I believe, right here, that much concentration. Well, if you were to try to find a K value for that, a Kc value for it, it would look like this. You'd have to take your hydronium concentration, you'd have to times by your hydroxide concentration, and then you'd want to divide by your initial amount, but keep in mind, liquids don't actually have concentrations. So watch this. If I were to take this number right here, which is 1 times 10 to the minus 7, and wouldn't the hydroxide be just as equal? So that would also give you 1 times 10 to the minus 7. What would happen when you times those 2 numbers by each other? 1 times 10 to the minus 14. Because isn't that how the exponents would work? The exponents add in that scenario. Minus 7 and minus 7 gives minus 14. Which is why water is actually considered to be the weakest of our acids. And this is what I'm going to get to slowly over time, is that your data booklet actually has what are known as Ka values, which are values very specifically for acids. That makes sense. And so what we're going to do is we're going to slowly work on that. Sometimes we'll actually call this one not Ka, we'll call it Kw. The W specifically meaning that it's the K value for water. And we'll do KBs for bases. Anyways, let me keep going back to my notes here because I'm getting a bit off task, but that's kind of our goal. That's what I want us to be able to kind of work with over time. So let's do some quick review, though, about properties of acids and bases first. So acids are sour, they conduct electricity, they have low pHs. Why do they have low pHs again? Well, remember, the formula was that your pH was equal to the negative log of your concentration. You guys recall that formula? And so the larger the concentration, what ends up happening is if you increase your concentration, it actually decreases your pH. So like the more hydronium you have, the lower a pH value you have. And the reason why is that's how a log number works. If you have 0.0002, like this is going to be a pH of roughly 2. And the reason I know that is because that's how many zeros you have in front. The number of zeros you have in front is a good indicator as to what the pH is. Why don't I flip to the next slide here? Bases then are kind of the opposite. These then have pHs that are high. Now, at the time, this didn't necessarily make a whole lot of sense because how can bases be on the pH scale? Isn't a pH a measure of how much hydronium you have? Why would a base have hydronium? Let's say that one more time. Why would a base have hydronium? Well, let's say we took kind of a very, very common base, like say NaOH. You'd have some Na plus, you'd have some OH minus. So yeah, clearly you'd have some OHs, right? And there'd be a whole bunch of those sitting in your beaker. But what did you make your base in? Water. Some molasses. I guess you could. But you made it in water probably, right? And by virtue of water being the aqueous, right? Because since you did NaOH in an aqueous state, you have water. And what do we know that water does? Well, water has the ability to break up into OH minus and make it even more basic, but also into some H3O plus. So there will be some H3O plus concentration. However, is this H3O plus going to stay that long? No. I mean, not only will there be these ones that it can run into and reform water with, but there'll also be these ones that it can form. But if you were to take like a magic snapshot of a basic solution, would you find a random H3O plus particle here and there? Yeah, you would. Okay. Which explains why we can actually have that pH scale there. Okay. I also threw a slide in here just to remind you guys how to name acids, just because you do need to know how to name them all properly. So quick review here. If you ever have a binary acid, that would be like the HCl or HF or HBr. Those are the ones that you call them hydro acids, like hydrofluoric, hydrobromic, hydroiodic, those acids. The technical term for the other one would be ternary acids. This would be like, say, H2SO4 or H3PO4. Ternary because you've got 3 species to them. And these ones are always the polyatomics. You guys remember the basic naming scheme here? So if it ended with an 8, 8s turn into X, and anything ite turns into us. So that's why I threw that slide on there. It's not really important to this. And then bases, you just name them based on how you see them. So most bases are probably going to be something hydroxides. They don't have to be. For example, just a little bit of review because it's been a while here. NH3. Is that a base? Well, it doesn't have an OH in it, but actually it is a base, and here's the reason why. When NH3 adds to water, do you guys recall doing this? What can end up happening is a hydrogen can leave the H2O and make it NH4 plus. Is NH4 plus actually like a valid polyatomic that you've heard of? Yeah, it's ammonia. What you're left with then is OH minus, and so yeah, look, I was able to produce something basic. But here's the thing, does NH3 and H2O stay this way? Well, actually no, because otherwise you'd have none of this left over. This would just all decrease. So what I hadn't shown you back in our first unit is that this is actually an equilibrium system. And these two guys will then recombine to form what you started with. Okay, so let me get to that water ionization concept, because although I've kind of hinted at this before, That's kind of the main point of my lesson today. The idea that 2 out of every billion water molecules will break up into an acid and a base. And then later they'll find another one and reform back together. And so that's this concept here, is that the Kc value for this would just be the final two things, because liquids can't actually have a concentration. You cannot have a concentration of liquid, because the way a concentration works is you must have a solute in a solvent. And liquids are just straight up one item. So this is your Kc value here. And we've discovered then that if, again, let me do this one more time here. If the pH is 7, it means that, well, actually, maybe I should do this. Do you guys remember the other formula? It was 10 to the power of negative pH was your hydronium concentration. You guys recall that formula? Again, it's been a while since we've done this, but that was the formula to calculate concentration. So if the pH of neutral water is 7, then your hydronium concentration is 10 to the minus 7. And that'll be the same thing for your OH concentration as well. So these will be the same as each other. So if this number right here is 1 times 10 to the minus 7, and this number right here is also 1 times 10 to the minus 7, that's where that value came from, the one I just showed you in your data booklet. So now, is that number greater than 1? Not even close. Well, what happens again if a Kc value is greater than 1? Yeah, it means you make a lot of products. Do we make a lot of products in this example? No, we barely even attempt to, right? So what we do know, though, is that this value right here is so small, and so therefore it really happens so infrequently. There we go. Here's kind of a visual picture of that exact same sort of thing here. 2 water molecules, they collide. Here's the percentage. It's less than 10 to the minus 6%. So it is exceptionally rare, but when they collide, a hydrogen basically pops off of this water molecule and makes you your acid and base. But we know that it's going to reform again. Here's your Kc value, except in this one right here I'm visually showing you, we can't count the liquids because they have no concentration. So this leads to some new formulas, and this is kind of the goal of my lesson today. We're going to do a lot of math calculations, trying to calculate one of 4 things. We're either going to try to calculate the pH, the pOH, or the hydronium or hydroxide concentrations. Those are the 4. So you're really looking for either this one here, or its doppelganger, the pH, or you're looking for the OH concentration, and its doppelganger, the pOH. Okay? And this is a new formula that we can now add to our lists. H3O plus and OH minus is equal to Kw, and we know that this number right here is 1 times 10 to the minus 14. I believe it actually lists this somewhere else in your data booklet as well. I don't remember which slide, but the 1 times 10 to the minus 14 number is on the acid table and somewhere else sitting in there. So it leads to these formulas. Let's say that you want to calculate a hydronium amount. All you've got to do is take a Kw and divide by OH. Because can you guys see how all we did is we just divided both sides by OH minus? And that got H0 by itself. Or if you want to get OH by itself, then divide both sides by H3O plus. And that's how this one was by itself. So we now have some new formulas to help us in some math equations. Okay. Here's the other formulas that we haven't used in a while. pH is the negative log of hydronium, and H3O is 10 to the minus pH. If I can give you guys some advice, write them in your data booklets because they don't give you these. Okay. So you need to memorize all these formulas here. They're not overly challenging formulas, but yeah, and I promise you, you're going to need to use them because that's a major outcome, is being able to calculate concentrations and pH values. Eventually, we're also going to throw in that table of Ka values, but that's my next lesson. I like this square right here. It kind of has like a nice visual to try to explain the 4 things I want you to solve for. You need to be able to solve for the hydronium or the hydroxides, or the pHs and the pOHs. And really, it kind of gives you some basic formulas on this one here for how to convert. But I think that's enough. Why don't I hop into an example? So try to find this slide here, and let's get to kind of the main point of my lesson now. Okay, so it says that we've got a 0.15 molar solution of hydrochloric acid, and it actually has a hydronium ion concentration of 0.15 moles per liter. I want to talk about that one for a bit here. If I were to make an ice table for how this would look, we haven't done this in a while, but here's the basic idea. HCl, as an aqueous format, is going to react. What does it react with? You guys remember? Water. And what's it going to form? Well, if it's going to be acidic, it's going to form H3O+, and then the other thing is going to be Cl-. Is Cl- a valid polyatomic that you've seen at some point before? Yeah, it's not even a polyatomic, it's just a basic ion. Do you guys remember doing this way back in September? This now proved that HCl was an acid. Previously to this, I just told you, hey, if it starts with hydrogen, it's an acid. But like that actually wasn't true. The reason why it's an acid is that when you add it to water, it can form the hydronium. Now, according to my ice table right here, there actually isn't really equilibrium going on because it says we started with 0.15 moles per liter of HCl, and then later the hydronium ion concentration actually was 0.15 moles per liter. How much is the most hydronium you could have made if everything reacted? 0.15, right? Like if all of this turned into this, it would have changed. So if I were to make an ice table, it would actually look something like this. 0.15, these guys started at 0. This one must have went up by 0.15, which means this one went up by 0.15, which meant this one ends up at 0.15, which means this goes down by 0.15, which means it ends at 0. There's no HCl left. Do you guys recall the idea of strong and weak acids? On this table right here, again, it's been a while, that's why I'm kind of doing a review today, but there were 6 acids that were considered to be, quote-unquote, strong. And the reason why they were strong is not because they're exceptionally corrosive, but is that they react almost all of the time. At one point, I might have talked about a percentage. Let me go back here. If the percentage was basically 100%, that's what made them strong acids. Vinegar, for example, vinegar only reacts about 5% of the time. And so the reason why this is strong is that it completely 100% reacts. And I can actually see that in the Ka value right here. The top 6 acids up here are considered to be so strong that they don't actually undergo equilibrium. The reaction just takes place at 100% of the time, and their Ka values, the reason why we don't even list them, is that they are basically so infinitively, I don't know, so large because really there is no equilibrium. There is no going back again. And you guys will notice that hydrochloric acid is one of those strong acids. And so I can't even calculate a Ka value. And let me show that to you back here again. Let's say I wanted to calculate the Ka value. Or I guess let's just call it Kc for now, because I haven't actually talked about Ka. But let's say we wanted to find the Kc value. We would put the hydronium concentration and the chlorine concentration over top of the HCl concentration. Remember, products divided by reactants. Why didn't I include water? And liquids don't actually have concentrations. Now let's say I try to type some numbers in here though. Well, this would be 0.15 squared all over 0. Can I actually divide by 0? No, it's physically impossible for me to do this, which is why the Ka value in your data booklet doesn't even exist, because there is no going back again. That doesn't even happen. So anyways, let's get to the point of my question now, though. Is it actually wanted me to calculate the hydroxide ion concentration, which again, some kids get a little confused and they go, Chris, we just finished talking about how this is an acid. It 100% of the time broke up. The word we used, by the way, was ionize. You guys remember the vocabulary from earlier last semester? It ionized 100% of the time, and it's only made hydronium and chlorine ions. But, hang on a sec, it was in water, and doesn't water have the ability to also ionize into hydroxide? So we're going to use one of those new formulas. I'll make a new page here. The formula was the Kw for water is your hydronium times by your hydroxide. And so there is water involved. So water's acid value, its K value, was 1 times 10 to the minus 14. If I want to try to calculate my OH value, all I need to do is divide by my hydronium concentration. But hey, didn't we have the hydronium concentration? Wasn't it 0.15? So if you replace this with 0.15, I need to grab a calculator. We should be able to calculate how much hydroxide there's going to be. Is there going to be a lot? Nope, like hardly any, but there will be some. So 1 times 10 to the minus 14 divided by 0.15. I got 6.6 repeating to the minus 17. So with sig digs, I guess I get 2 sig digs. So I've calculated a hydroxide concentration of 6.7 times 10 to the minus 14 moles per liter. Did you guys get that too? Oh, what did I say? Oh, to 14, sorry, 6.67 to the minus 14. So do we have a high concentration of hydroxide? No. But if you were to look inside an acid, would you find a few random OH particles? Yes, you would. Why? Because of water. 2 times in a billion, water breaks up into H3O plus and OH minus. That makes sense? Sure. No? Yes? Give me some feedback, guys. Okay, let's try another one. Let's try to find the concentration of hydroniums in barium hydroxide. Now, this one's tricky for a couple different reasons. First one here is if I want to make some sort of like ice chart like this. It works a little bit differently this time around. Barium hydroxide would be BaOH2. And it's a bit different because this is an ionic compound. HCl was molecular, but this one's ionic. I don't need to add this to water. I know it will be in water, but I can literally just dissociate it into Ba2 plus ions and into 2 OH minus ions. And a lot of kids will forget about the 2 right here. Because here's what happens. This is also not going to be at equilibrium. Ionic substances, when they dissociate, they're going to dissociate 100% of the time. Okay? Molecular things might be at equilibrium once in a while, but this is going to be a 100% dissociation. And so that means that if I were to make an ice table, but I'm not going to bother, it would start off with 0.25 right here, and we're going to make this stuff over here, and there'll be none of this left. But I guess the real point I'm trying to make is that if I start with 0.25 moles per liter of this, how much hydroxide am I going to actually make? Twice that much. I'm going to make 0.50 moles per liter of this. Fair enough? So, now, then again, someone would ask, well, then, Chris, why is there hydronium? Don't forget, these were aqueous. So there is water. So again, if I were to draw like a bit of a picture of this. Please excuse the interruption. Junior high teachers, can you please do your first block attendance? Junior high teachers, please do your first block attendance. If I were to draw a picture of this on a smaller scale, for every 1 barium, there'd be 2 hydroxides sitting in there, right? However, don't forget, there was also a little bit of water sitting in here as well, right? And on rare occasion, I'll have to draw it outside the picture, the water had the ability, 2 of them, split up into an H3O plus and an OH minus. Is this guy going to last long? Well, normally it wouldn't have, because even just in regular water, he'd have found another hydroxide to react with and reform water. But it's going to be even less so in this container here, because this is a very hostile environment for that H3O. I should say that again. This is a hostile environment, because not only is there this OH trying to reform it, But there's like all of these guys that as soon as it runs into one of those, it's going to remake water. But would you find a hydronium? Yes. You'd find a few random ones. So here's how you're going to solve this one here then. Same thing as before. You're going to say to find an H3O concentration, you just need to take your Kw and divide by your hydroxide concentration. But the reason why people might get this one wrong is they might divide by this concentration, not by the doubled concentration. So take 1 times 10 to the minus 14 and divide by 0.50. Let's not spell that. So divide by 0.50. I got 2 times 10 to the minus 14. So with sig digs, I need 2.0 times 10 to the minus 14, and that would be my hydronium concentration. You guys able to follow that? Okay. So now I want you to actually calculate both the hydronium and the hydroxide ion concentrations. And I gave you a little bit more information though this time. I said that we're dissolving 2.6 grams of sodium hydroxide in half a liter of water. So again, this really pulls on what we learned way back in September, October in the first couple months of our course. Because before I can even get to finding the concentration amounts, I have to kind of figure out the grams to moles conversion. Because this time around, I gave you 2.6 grams. That's not actually where we normally start. So you guys know sodium hydroxide's molar mass. It's at 2299, 16, and 101. It's 40 right on the dot. So if I wanted to try to calculate my concentration, it would be 2.6 grams. We'd have to divide by my molar mass. So I calculated 0.065. And then that's going into half of a liter. So I've calculated a concentration for your sodium hydroxide at 0.13 moles per liter. Is able to follow that? I took the mass, I divided by the molar mass. It's going to get harder to write on this program than my normal one. So I took the mass, divided by the molar mass to get this moles number, divided by the liters, and I found the concentration of sodium hydroxide. Now, you won't do this process every single time, but you'd now have to ask yourself, is sodium hydroxide ionic or covalent? It's ionic. Ionic things completely dissociate. Okay, we don't have to worry about strong or weak ionic things. We do have to worry about strong or weak molecular acids and bases where they may not 100% ionize. But this one right here, if I were to write out my equation, would look like this. NaOH is going to dissociate into Na plus and OH minus. I don't actually have to add this one to water, unlike the acids. I do need to add them to water. And so if I start with 0.13 moles per liter of this, I'm going to end up with 0.13 moles per liter of hydroxide. So that's good. Be careful though. I've seen them throw this in a diploma question before where it's like, say, barium hydroxide. And if there's a 2 in front of this, you have to double it. They love to throw that in there to mess with you. So, okay, so actually I'm done one of them. I now know the hydroxide ion concentration. So if I want to write it off to the side, the hydroxide concentration is 0.113 moles per liter. And if I want to find the hydronium one, this one's probably getting a little bit easier by now. All I've got to do is just take Kw and divide. So 1 times 10 to the minus 14 divided by 0.13. With sig digs, I get 7.7 times 10 to the minus 14 moles per liter. Which hopefully makes sense because I have a relatively high concentration of hydroxide. I actually have a really low concentration of hydronium. Now, I want to try one more thing, even though this wasn't my question here. You guys remember how to find pH and pOH? You use the formula negative log. So what I'm going to do now is I'm going to negative log both of these numbers. And I'm going to calculate my pOH and my pH. I'm just going to do this to make a point here. So if you negative log this one, I got a pH of 13.11. Do you guys remember the rules for pH, for sig digs? Why did I keep 4 digits? On pHs, the first 2 numbers don't count. Okay, the only numbers that count for sig digs on a pH is the numbers after decimal place. So if this had 2 sig digs, this one and this one right here, those count as your sig digs. The 13 doesn't actually count for sig digs. If I negative log 0.13, I would get a pOH of 0. Let's call that 89. We only did this briefly back in September, October, but these two numbers right here, what do they add to? 14, which kind of makes sense in a way because wasn't neutral on a pH scale 7? And so in a way, if you were to add your collective amount of acid and your collective amount of base, it should actually add up to 14 when you're done. Okay. If you guys can follow and do what I did right here, you've more or less got my point for the day, which is I need you to be able to calculate the 4 main things. So if I go back to that triangle, that square that was back here, I need you to be able to calculate OH, H, pH, and pOH. And that's what we've now done in this example here. I've now calculated a OH concentration, which is fairly high, which meant a low pOH, and a hydronium concentration, which was very low, which meant a high pH. If you can do all 4 of those, we're good. That makes sense? Okay. So let me kind of summarize where this finally finishes then. The whole idea then is that we can talk about acid and base strengths based on equilibrium. We had previously learned the idea that strong acids react like all of the time. Like for example, HCl. HCl turns 100% of the time into H plus and Cl minus if I want to take that the shortcut way of writing it. However, acetic acid, which is CH3COOH, it didn't react 100% of the time. It reacts like 5% of the time into H plus and CH3COO minus. But now I can explain a bit of a better reason as to why. It actually reacts all the time. The only problem is that it starts turning back into what it began with. And so it's not that it was a hard reaction to perform, it's just that these guys right here like to re-get back together. I use that analogy of that bad teenage TV rom-com where, you know, they're together in season 1, they break up in season 2, they're back together in season 3, they break up for 2 days in season 4, then they have a one-night stand in season, you know what I mean? Like, that's kind of the idea here, is that it tries to break up and it re-gets back together again. We can now classify strength based on not only just this percentage, but how well it affects, how well it works at equilibrium. So if I can go back to that table I showed you guys, which I've been kind of doing here, there are 6 known strong acids, these 6. They are strong because they don't actually undergo equilibrium. When this thing right here reacts with water, it will form what's known as its conjugate base. We'll get into that terminology later. But this guy right here is going to lose its hydrogen and turn into this stuff. And it does it all of the time, and it never gets back together. So this is like Taylor Swift. We are never... Come on, that was good. Right? So when these guys right here break up into this plus a hydrogen, they stay that way. Whereas these ones down here, when this acid tries to turn into this one plus hydronium, it actually reforms again. And what we really have here then is, if you like to use that, I don't know, I'll use the Taylor Swift analogy here, of who is willing to like get back together. Went way too far here. Water. Water doesn't hold out very long. As the water tries to turn into the OH minus, 30 seconds later, it's like, no, let's get back together again. Right? And that breakup lasted all of like a short while, right? Whereas as you go up the list, that's why we call it strength, because the strength, I guess, is in the ability to stay separated. These guys up here at the top always stay separated. These ones down here, they start to separate, but they eventually start going back together again. All right, back to my notes. I'm almost done, aren't I? What do I got left? Just a few more examples. Okay. So this is kind of what I've been discussing the whole time then. If we have a quantitative reaction where it occurs almost all of the time, it's not at equilibrium. So really, we're not going to focus on those often, but it could come up. What we're going to focus on more is the ones where you have like a 1.3%. Here's what I want to do. I want to show you guys a lead-in to kind of our next lesson. We're going to talk about how to calculate concentrations based on those Ka values. So let's use acetic acid here. Is this my last one? No, two last ones. Here's acetic acid. Let's say that I give you a 0.10 mole per liter solution of acetic acid. But I tell you that acetic acid is weak. Because really what tries to happen here is that the CH3COOH reacts with water and it breaks up. It breaks up into H3O plus and CH3COO negative. But this was not a permanent breakup. They got back together like almost immediately. And I know that because I told you there's a 1.3% here. If I were to make my ice chart, though, it would look something like this. We started with 0.10 right here. And water doesn't count because, well, water's a liquid. Water doesn't have a concentration. And we didn't really begin with anything here. This is where I'm kind of coming full circle because this is why I started my lesson with an example. What's going to happen to the stuff over here on the product side? Is it going to go up or down? Well, it has nowhere to go but up. But I don't know how much it went up by, so I'm just going to say it went up by an unknown amount of x to finish at this amount right here. And what's that going to mean about the acetic acid concentration over here? Well, it means it must have gone down by x to finish off at 0.10 minus x. Now, I know that only about 10% of this turns into the stuff over here, but I actually have a better way of calculating this now. If you guys go to your data booklet, find acetic acid, which I believe is just slightly underneath the fold of your page. Can you guys see how there's a K? We call it a Ka value, specifically because it's an acid, but I actually know its value. It's 1.8 times 10 to the minus 5, which is really low. So if I were to go back over to here, I can now tell you that the Ka value, which is really just Kc, it's the same thing, was 1.8 times 10 to the minus 5. But I can actually use that to calculate my x values, because my x value is really going to be x squared all over 0.10 minus x. So by looking up a value in my data booklet and making a really quick little ice table here, I should be able to tell you how much hydronium I have left, because isn't when I solve this for x, isn't that going to give me hydronium? I'm going to see whether I can snap this into a new page here. Add to new page. There we go. Cool. All right, how are we going to have to solve this? Math. What do? How do you do with anything with fractions? You need common denominators, and if you have that, you need to cross multiply. So this denominator down here, I'm going to cross multiply it up over here, which means I'm going to get 1.8 times 10 to the minus 5 times by 0.10, and then I'm going to subtract 1.8 times 10 to the minus 5x, and that'll all equal x squared. You guys follow that? This number here has to times by the 0.10, and this number right here also has to times by the x. So 1.8 times 10 to the minus 5 times by 0.10 actually makes this number 1.8 times 10 to the minus 6. This number is just 1.8 times 10 to the minus 5. That's how many x's you have. Where am I going with this? How do I solve this thing? Yeah, or you can graph it, by the way. If you know how to use your graphing calculator, you can do that. But they give you the quadratic formula for a reason. So I'm going to swing everything over to this side right here and make it x squared plus 1.8 times 10 to the minus 5 x minus a constant term of 1.8 times 10 to the minus 6. But I should be able to solve this. I just need to use the quadratic formula. It just means that my b and c values are ridiculously small, but that's okay. I can still do it. So quadratic formula is negative b plus or minus b squared minus 4ac all over 2a. I know you guys have the skills to do this because you've all done 20-1 math, right? So it's just a matter of not making a mistake with the fact that you're using infinitesimally small numbers here. So, we're going to get two answers. One of them is going to be extraneous, so I'm just going to get started. 1.8 times 10 to the minus 5 plus the square root of 1.8 times 10 to the minus 5 squared minus 4 times 1 times 1.8 times 10 to the minus 6. And screw that up there. Oh, there's a minus sign there. And then all of that is divided by 2. So I did it and I got this number here for one of my answers. 0.00133. I'm going to try the other version just to see whether I get something useful there. Subtract, divided by 2. The other one I got was negative 0.00135. So I'll pause for a bit there. Let me know if you guys can't calculate those values yourselves. Everybody okay with being able to do that that's tried it? Graphing it can work. The only downside is that the scale of your graph is like horrible because of the fact the numbers are so small. As those ones there? Okay, I'll come take a look at yours later then. Graphing it should work though. Everybody else that tried it algebraically though got this? Okay, so we're not done by the way. I'm going to go back a slide here. It said to calculate the hydronium ion amount concentration, which is really what X is. And what did we get for X? Well, we got, the only one that really works is this one right here, the 0.00133. So if I go back over here, this number right here must have been 0.00133. Which, I gotta be honest, I actually took a really long time to do a question that could have been much shorter. Because didn't it tell me that only 1.3% of this changed? You guys can do this in your heads, right? If you took this number here and times it by 1.3%, isn't that what that was going to be? So now that being said, they normally don't give you percentages like this. They normally give you Ka values and you solve it the other way. So, but this is kind of what we're going to build up to. That's kind of my main point tomorrow. So I'm going to kind of show you some examples today on how to do this, and I'm going to do more examples on this later and kind of build on the concept. So let's try one last one, then we'll call it a class. Where's my last one here? There it is. So we've got a pH of methanoic acid, and it's at 0.10 moles per liter when we started. We want to calculate the percentage. I'm going to kind of work backwards here. So what I could do is begin setting up my table. For example, methanoic acid is HCO COOH. That's methanoic acid's formula. Because methanoic acid would be like one carbon, double bonded to O to H, and you'd have a single hydrogen there. So that would be it. We would add it to water. It would, in equilibrium, form H3O plus, and it would form HCOO, which it is a valid polyatomic, by the way. Sometimes we write it as COOH negative. Either one works. Now, in terms of some of the values I've been given, this one right here is 0.10. And water we don't care about because it's not able to change its concentration. I was given another number here, though. I was given a pH value. Well, I can do a little bit of work off to the side then, because 10 to the power of negative pH is how you can calculate an acid concentration. So if I go 10 to the minus 2.38, that will actually give me how much acid I made. So 10 to the power of negative 2.38 gives me 0.004168, something like that. That's going to go here, 0.004168. Did all of this turn into this? No, not at all, actually. Only a small percentage of it did, looking like it's about 4.2% probably. If I want to complete the ice table, though, I could just for the practice here, because really this would have started at 0 and went up by 0.004168. And this alternate ion, whichever way you write it, would have also started at nothing and gone up by 0.004168, ending at 0.004168. Now, this is kind of a weird anomaly, but I want to make sure I show you it now because it's going to come up again more later. It means that this guy must have lost 0.004168. However, based on sig digs, here's what number would go there. And the reason why is that when you add and subtract sig digs, you always cut off at the least number of precision decimal places you have. And so it's kind of a weird anomaly here because clearly you started with something and you are losing something. But the amount you lost is so negligible that really how much you're finishing with in the bottom column of your table here is really the same thing you started with. The example sometimes I would give, you guys ever watch, Scrooge McDuck? The character there has a big money bin full of money. He has so much money that if you were to reach into the money bin and steal 5 coins out, okay, he might notice because he was really particular, but like, you wouldn't really notice at that point because it's like such a negligible difference. Now, to these guys over here who literally have nothing, if they stole 3 coins from Scrooge McDuck, it makes a huge difference because you're going from nothing to something. But for the guy who has $10 billion and loses $3, he really still has $10 billion. Does that make sense? Anyways, if I want to figure out my percentage, it would basically be this. It was 0.004168 out of 0.10, because this is what I made out of what I could have made. So if I want to calculate my percentage, this is how I do it. So that number divided by 0.10 times 100, and yeah, it's exactly what I think I said it was going to be. It's about 4.2%. However, I want to do one more thing while I'm finishing things up, and then we'll call it a day. We should also, though, be able to calculate a Ka value for this, because the Ka value would be these two guys right here divided by this one. So it would have been 0.004168 squared, because there's really 2 of them here, all divided by 0.10. So if I do that, I got this value here. I got 1.7 times 10 to the minus 4. On your data booklets. Hope this worked. It's always off by 0.1 if you have to do this. Methanoic acid is right here, also known as formic acid, and its Ka value. Oh, I was off by 1 decimal place. It was we did 1.7, right? Here, 1.7. This one's 1.8 times 10 to the minus 4. So that hopefully kind of comes full circle. There's two types of problems I can give you. I can either give you numbers and you calculate for me a Ka value, or I give you a Ka value out of your data booklet and you work backwards and try to calculate some sort of unknown concentrations. And that's kind of our main goal, is building up to being able to use, I guess, the following things. You have to be able to use your H3O and your OH minus formulas. You got to be able to use your pH and your pOH formulas. And you got to be able to use this new formula finding Kc, where you take your products and divide by your reactants. Either a Kc value will be given to you, or you're solving for a Kc value. One of those two. Okay. This unit, I would say, is about a 50-50 split. It's either going to be some theory, like say Le Chatelier's principle, where it asks you, okay, if you increase the volume, will it shift that way? If you decrease the temperature, will it shift this way? But a good chunk of what you're going to do, this is a very math-intensive unit. You do a lot of calculations in this section. So, okay, that's it for now. It's kind of only half a lesson because I'm really going to build on this again tomorrow. But do you guys have any questions for now? Yeah, totally. Where did I finish off there? Right about there? Just leave it there. Any other questions? In terms of things you guys can work on then, you're getting close to being able to start doing some of the assignment questions, but I'd probably just suggest with whatever time you guys have left over, finish up your, you do your lab first, I think. And we'll get to the assignment later. I do want to teach a few more things and show a few more little intricate details or little like one-off anomalies. So, okay, I'm done then. Thanks, guys.